Good morning, everyone. And today I will be presenting a container replication mechanism called RRC that provides low overhead and fully application transparent fault tolerance for critical server applications. This is a joint work with my PhD advisor, Yuval. So server applications demand low latency, high throughput, and high reliability. And as a result, server applications is generally multi-threaded, and they require some sort of fault tolerance mechanisms to provide high reliability. The fault tolerance mechanisms requirements for a server application is that it needs to maintain low latency and throughput overhead, while also support multi-threaded. And ideally, a fault tolerance mechanism should minimize the development cost. This means it should not introduce any code modification to the clients and to the servers. It should maintain fully compatibility with the existing clients. So in other words, the fault tolerance mechanism needs to be application transparent. And a widely used mechanism to achieve application transparent fault tolerance is through replication. So here's an overview of how it works. The clients communicate with the server applications in the primary host. And the replication mechanism ensure that the server application in the backup host has a consistent state with that in the primary host. And as a result, if the primary host fails, the clients can directly communicate with the server application in the backup host and without being affected. So replication is a widely used old technique, and it has been deployed since the 1960s, if not earlier. But what is missing with the existing replication schemes? For many older schemes, they require customized hardware, and there is no support for multi-threaded applications. There is a class of schemes based on checkpointing to a passive backup. However, this scheme incurs unacceptable high latency overhead for server applications. Another class of schemes is based on active replication, and they are vulnerable to non-deterministic events, and this causes unpredictably slowdown during normal operations or even recovery failure. Furthermore, with active replication, the performance of the whole replication system is limited by the tight coupling among replicas, so a slow replica may slow down the whole system. The RRC mechanism I'm going to present today overcomes these above limitations with a key insight to decouple replication-related operations from normal operations. So I'm next going to present the limitations of the existing replication mechanisms, which forms the motivation for RRC. So one class of the replication mechanism is based on checkpointing to a passive backup, and here is how it works. The execution of the application is divided into multiple epochs. And during the execute stage of one epoch, the application executes, but the output to the clients is being buffered. And then, at the end of the epoch, a checkpoint is taken. The application then resumes execution, and the replication mechanism sends the checkpoint to the backup host. The backup host acknowledges the receipt of the checkpoint, and only until then, the output to the clients can be released. The buffering and releasing output is needed to ensure that upon primary failure, the backup can restore to a state that is consistent with the clients. And a critical drawback of this mechanism is the high latency overhead. So specifically, output generated during the execution phase of one epoch cannot be released until the backup has acknowledged the receipt of the checkpoint. And since checkpointing is an expensive operation, there is a critical trade-off involving checkpointing, where a short interval leads to high throughput, low latency overhead, while a long interval leads to low throughput and high latency overhead. In reality, the replication mechanism can only afford a checkpointing interval of tens of milliseconds, and this translates to at least tens of millisecond delay, which is unacceptably high for many server applications. Another class of the replication mechanism is based on an active backup. In this case, both the primary and the backup execute application code. And instead of sending a checkpoint at the end of an epoch, the primary contiguously sends the outcomes of non-deterministic events it encountered during execution to the backup. And backup uses the event log to replay its execution to match that of the primary. And since with the active backup mechanism, the backup execution must be consistent with the primary. If the primary fails to track certain undeterministic events, such as data races, then this would lead to unpredictably slowdown during normal operation, or even recovery failure. Furthermore, with active backup mechanism, the performance is always limited by the tight coupling between replicas. A slow replica may slow down the whole system, and the resource overhead due to execution replay is at least 100%. So why existing replication mechanism have all these limitations? And we believe the root cause is the coupling between replication-based operations and normal operations. So specifically for the passive backup mechanism, I have explained the coupling between checkpointing interval and delay in releasing outputs. Furthermore, to take a checkpoint, the application has to pause, and as a result, there is a coupling between the time to take a checkpoint and with service interruption. For active backup mechanism, there is a coupling between unchecked non-determinism and service interruption. And also, the performance on the primary is coupled with the performance on the backup. And a key insight for RRC to overcome these limitations is to break all these existing couplings. So I will next present how do we make design choices in RRC that performs the decoupling while overcome the limitation. So we start RRC's design by choosing a passive backup. This is because compared to an active backup mechanism, the passive backup has fundamental advantages in terms of avoid vulnerability to non-determinism, avoid performance coupling, and also reduce resource overhead. And as I have just explained, a critical drawback of the passive backup mechanism is the high latency overhead, and the root cause is the coupling of latency overhead and checkpointing interval. So RRC performs the decoupling with a replication scheme that we call hybrid replication that combines the checkpointing in a passive backup with execution replay in an active backup. With hybrid replication, output released is thus decoupled from checkpoint commitment. And this is possible because upon primary failure, the backup can restore to a state that is consistent with the client by first restore the last checkpoint, and then replace the primary execution up to the last released output to the clients. Replication can be done at zero granularity. It can be done at the virtual machine level, at the process level, and at the container level. For virtual machine, it has this high runtime overhead, and furthermore, applying the hybrid replication to virtual machine would be challenging because this would require checking non-deterministic events in the OS. While for process, it has this typical problem of naming conflicts upon failover. And as a result, RRC chooses to replicate at the container level, which resolves the limitations of process and VMs. So with all that, so here's an overview of how RRC works. So with RRC, the critical server application is deployed in a container in the primary host. And the execution of the application is similarly divided into multiple epochs. During the execute stage of one epoch, RRC redirects client request to the backup, and it's being recorded in the backup. And then the request is sent to the application in the primary host. The application executes and generates a reply to the client. It will also be sent to the backup and being buffered there. The application later sends a non-deterministic event log that can reproduce this generated reply. This will be sent to the backup, and upon the backup receiving this log, it then releases the reply to the clients. Also, at the end of each epoch, a checkpoint is taken and sent to the backup. So here is how RRC handles the primary failure. If the primary fails, the backup first restores the application state from the latest checkpoint. The backup then sends the non-deterministic event logs and the recorded inputs from the clients to the application. The application then performs execution replay to bring its state consistent with the failed application state in the primary. And then this application in the backup can continue service the clients. Since RRC redirects the reply and the request through backup, it must also handle backup failure. If the backup fails, the application in the primary advertises the service IP address so that the clients will directly send requests to the application in the primary host. And the recovery can thus be finished if and the application directly sends the reply to the clients. So I have just presented the core design aspect of RRC. For RRC to function correctly, we need to overcome a list of the design and implementation challenges. And here is the complete list of them. And due to time limitation, I will just focus on the first two items. So as I have just explained, RRC performs periodic checkpointing at the end of each epoch. And checkpointing requires saving a consistent state. And as a result, execution must pause during checkpointing, and this leads to service pause time. Since RRC chooses to replicate at the container level, and a critical issue here is that the container has tight state coupling with the underlying kernel. And as a result, when you need to take a checkpoint of the container, significant in-kernel container state must be checkpointed. And with the current Linux, retrieving such state is slow. It takes thousands of system calls. So as a result, checkpointing a container is slow. So thus, a key challenge RRC overcomes is to minimize the pause time despite slow checkpointing. And RRC achieves this by decoupling the retrieval of in-kernel container state from container execution. And to achieve this, RRC introduced a new kernel primitive called container fork. The container fork creates a clone of an existing container. And with the container fork, when RRC needs to take a checkpoint, it first pauses the application container, and then uses the container fork to create a shadow container. The application container can then resume execution, while the checkpoint is obtained from the shadow container. And the container fork significantly reduces the service pause time of our benchmarks by an order of magnitude. Another challenge RRC must to overcome is the non-deterministic events. So specifically, since, as I just explained, RRC is a hybrid replication scheme, and it only requires execution replay during recovery. And as a result, it is only vulnerable to non-deterministic events occurring during the epoch of failure. And to handle non-deterministic events, RRC requires on the non-deterministic event logs it obtained from the primary. With multithreading, memory access ordering is non-deterministic, and thus they must be checked. So a straightforward solution is to record the order of all memory access. However, this incurs unacceptably high overhead due to the frequency of memory access. So instead, RRC chooses to record the outcomes of synchronization operations. This can guarantee the correct replay as long as the programs do not have data races. And by data races, I mean memory accesses that are not synchronized by synchronization operations. And thus, RRC need to handle data race. So there are several key characteristics of data races that guide RRC's handling of them. First of all, data races are bugs, and programmers generally try to avoid them. However, it is impossible to eliminate all data races with languages like C and C++. Fortunately, existing tools can effectively detect frequently manifested data races. And for deployed server applications, they generally go through several rounds of testing and debugging. And as a result, it is expected that frequently manifested data races are unlikely to exist. And as a result, RRC focuses on infrequently manifested data races. And the way RRC handles data races is motivated by a common scenario occurred during replay, which is during the replay on the backup, most of the system calls are not actually executed, but just being replayed. And as a result, this will cause a significant different timing of thread execution in the record run compared to a replay run. And such different timing of thread execution is likely to cause different outcomes of data races, and as a result, different outcomes of replay. So the RRC's mechanism to mitigate the impact of data races is first, during the record run, it will record the time intervals between system call returns on the primary. And then the recorded time interval is sent to the backup together with the non-deterministic logs. During replay, the backup informs the system call time interval and thus causes a similar timing of execution compared to a record run, and thus the same outcome of data races. While this mechanism does not guarantee correct replay in the event of data races, we find it pretty effective to handle real-world data races which are infrequent. Specifically, with two of our workloads which has infrequent data races, this mechanism can boost the successful replay rate to over 99%. So with that, I'm going to present the evaluation of RRC. So we perform extensive evaluation on RRC, and due to time limitations, I will just focus on the first three items. So we compare RRC against NiLiCon, which is a state-of-the-art container replication mechanism based on checkpointing to a passive backup. And we use server workloads, in-memory databases, and web server to evaluate RRC. And we configure RRC to take a 100 millisecond checkpointing interval. And here is the latency overhead comparison between RRC and NiLiCon. And in summary, RRC achieves an average latency overhead of less than 300 microseconds, while for NiLiCon, it is tens of milliseconds. When it comes to the 99th percentile latency, RRC is still below 1 millisecond. So in summary, RRC achieves 2 orders of magnitude lower latency overhead. And the main contributor of this is the hybrid replication that reduces the average latency overhead, and the container fork that reduces the 99th percentile latency overhead. And here is a throughput overhead comparison between RRC and NiLiCon. The y-axis is workloads, and the x-axis is the latency overhead. We divide the sources of throughput overhead into 3 categories. The first one is due to recording non-deterministic events. And the second one is due to the container pause for checkpointing. And finally, the third category is due to copy on write after container fork to maintain state consistency, and the page fault that check 30 pages for incremental checkpointing. And comparing RRC against NiLiCon, RRC has the extra overhead of recording non-deterministic events. However, thanks to the container fork, RRC has a much smaller pause overhead. And this, in return, translates to a significant advantage in terms of the overall throughput overhead. And we performed thousands of fault injections, and we inject fail-stop failures to evaluate the success rate of RRC. And to stress RRC's recovery mechanism, we perform injection into both the primary and the backup host. And here's the result. With real-world examples of data races, RRC can achieve a greater than 99% recovery rate, and RRC achieves a 100% recovery rate if the applications are free of data races. So to summarize, the key goal of RRC is to provide application transparent fault tolerance for server applications, It requires support multithreading and minimize the latency and throughput overhead. The key insight in RRC to meet the design goal is to decouple replication-related operations from normal operations. So specifically, RRC introduced the hybrid replication mechanism that decoupled the checkpointing interval from delay in releasing outputs. RRC introduced the container fork mechanism to decouple the time to take a checkpoint from service interruption. And RRC uses a passive backup, which has fundamental advantages to handle unchecked non-determinism. And furthermore, RRC introduced a timing adjustment mechanism that can mitigate the impact of data races. Our evaluation results shows that RRC can achieve 2 orders of magnitude lower latency overhead and significantly lower throughput overhead compared to state-of-the-art container replication scheme. When it comes to recovery rate, RRC can achieve greater than 99% recovery rate with real-world examples of data races, and 100% recovery rate if the applications are free of data races. So with that, thank you, and I'm happy to take questions.